Hello everyone, and welcome back to the course on external chemistry. Yesterday we have gone through some basic concept of PE, and there we have seen that as we know that pH is one of the very crucial variable in controlling the hydrolysis behavior of actinide ion in the solution. Similarly, we thought of a variable that can be called as PE in a very similar way that we call like pH. That is nothing but pH is minus log of hydrogen ion activity or concentration value. Similarly, suppose you can have a variable that is called PE. That is again, it can be very similar to the pH, can be minus log of electron activity. So we assume that suppose such a variable exists and somehow we can measure this for a system, then this will tell about the reducing or oxidizing nature or the reducing or oxidizing capacity of the medium. And then we have tried to see that how we can drive different relations between PE naught and the nature of, or you can say the composition of the solution. So here we have started with the half cell reaction and we have gone through all these calculations so that we could reach to this final equation. And if you see this equation very carefully, here we are relating our PE with the composition. So you can say depending on your oxidized species and reduced species. So if you know this, your concentrations of oxidized species and reduced species, you can have some idea about PE. In a very reverse way also, you can say if you know the PE, you can have some idea about the composition. And then we have compared it with the Nernst equation and we have derived certain relationships like this one or this one, where you can see that in some of the slides you will feel that I have given the term EH instead of purely E. It is just to make you remember that in all these calculations, rather I should say that it is your E naught is basically with respect to the standard hydrogen electrode. So because of that, we have given the notation H. So many times I've used this H also. So it is not very difficult. You can just say that it is just to show the relationship that with which respect you have measured your potential. So with this, we have seen that we have a set of half cell reactions whose standard electrode potential as we have measured with respect to SHG, they are known. And if you know this, then from here you can just simply use this equation, that is ln k is equal to minus E naught F divided by RT, and you will get the value of K. And this is the K value. And when you know this K value, you can easily calculate what is PE naught. That is nothing but log of K divided by N. So you can calculate this value, and again you can fit it into this equation that we have derived. And from there, you can use these relations to draw your EH-pH diagram. And we have also seen that what are the conditions, or rather I should say what are the boundary conditions that exist when you are using water as a medium. These conditions arises mainly because the water, as you can see, can oxidize. Suppose you have water, it has both the limit. It can oxidize to O2 and it can reduce to H2. So these are the limits or conditions that water can undergo, and because of that we should work in the conditions which limits these reactions. We should not be having a condition where water is getting oxidized to oxygen or it is getting reduced to the hydrogen. So based on this equation, these are the reduction equations, we have derived two relationships. P is equal to 20.75 minus pH, and here we have seen that the slope is minus 1. And here also we have derived the equation for the reducing limit of the diagram, and there also we are getting slope of minus 1. And here we can see this is our conditions. This is our oxidizing condition. Above this line, the activity of oxygen is more than 1. Similarly, below this line, this is the reducing limit of the media. Below this line, the activity of hydrogen is 1. And all the reactions, when we are considering the water medium, should be happening inside this zone. All the reactions should be inside this zone. And then we have seen that when we use the equation that we have derived, that P is equal to P naught plus 1 by N log of oxidized species divided by reduced species. Then we can use this equation and we'll get a different lines in the pH PE diagram. And again, this is your oxidizing and reducing limits. And then we have talked about two kind of line and then area. The first thing you can say, the lines can be horizontal, the lines can be vertical, or the lines can be slant. When we talk about the vertical lines, these are pure acid-base reaction and they do not depend on the potential. When we talk about the horizontal lines, they show a pH independent reaction. And these lines, when you see the boundary lines, suppose you have seen this line, the activity of these two are same on this line. So you can say they mark a place where the two species exist in equilibrium. Then we have also discussed about the area. Larger the stability area or larger the area a species will occupy, more is the stability of that particular species. And with this knowledge of EHPH diagram, we can understand some redox chemistry of the actinide into the environmental media. Because if you see the pH, the ranges are from 2 to 12, which is obviously your environmental pH should come within this pH. Similarly, your EH ranges are also in a range where the environmental EH comes into picture. So with this knowledge, can we draw, because this I have shown you for neptunium, but can we draw for other metal ions? So this is the list I have given you for different actinides starting from actinium to nobelium. And you can see that for all these actinides, I have given you the standard potentials. And as I've told you in the previous slide that if you have information about this standard reduction potential, you can easily derive the LNK values. And once you have this LNK value, you can use these two equations. You can derive from this LNK, you can derive PE, and that PE you can put it here, and then from this PE naught, you can derive an equation between PE, and depending on the reactions, suppose your reaction does not have any hydrogen in that, then obviously the pH term will not come to the picture. And similarly, if your equation does not have any electron term into that, then PE term will not come into the picture. So suppose you take a reaction, suppose this one I take, in which both the things are there. You have a proton, you have an electron. So for such kind of reactions, you will get equation which involves both PE as well as pH. So you can draw, you don't know the equilibrium, you can easily draw the lines for the pH-PE diagram using this set of equations. Why these equations or why these lines are very important to us? So when we talk about the redox chemistry, we all know that this kind of series that I've given here, it is very useful when you plan to have an experiment in which you are trying to oxidize or reduce a species using some reductant on oxygen. For example, suppose I have a species that is NPO2 plus and I want to reduce it to neptunium 4. So for this reduction to be feasible, I want a couple which can facilitate this reduction. So by looking the standard potentials, you can choose the two couples and you can add them and you can see that how the reduction is taking place or in presence of which couple is more favorable. But we have to see that, as we have seen that these are all reduction couples, and you have to see the delta G values, that is nothing but minus NF E naught. And so the two reactions, you have to see whose E naught is more positive. Suppose E naught is positive, it means delta G is more and more negative. So that reduction is more feasible. So if you have a couple whose reduction is more feasible compared to other couple, then obviously the couple whose reduction is more feasible will go into the reaction rather than the one whose reduction couple is not comparatively not feasible. So based on that, we can choose different couple and we can carry out this kind of reduction reactions. They are very important. And one of the examples I just want to discuss is that for neptunium again, for neptunium 5, we use a ferrous sulfamide. And if you see this couple, Neptunium 5 to Neptunium 4, in the presence of acid, you have to take care of that also. In the presence of acid, it is roughly 0.74. And if you see the iron couple, it is from iron 3 plus electron to iron 2 plus. This is 0.7. So this reduction using iron of Neptunium 5 to Neptunium 4 is not looks very feasible in this. As you can see from the couple, this is giving you more negative delta G value compared to this one. So in those conditions, what we generally do, as I've written, we use a complexing agent that is called ferrous sulfonate. What the complexing agent will do, it will try to change the thermodynamics of the reactions. What it will do, during the reaction, it will react with both iron 3 as well as Neptunium 4 to facilitate the forward reaction. So even in situations where the reduction couple is not that feasible, we can try to do the reduction just by adding some kind of complexing agent. So these complexing agents, these protons, everything that you are having in the medium has some effect on your E naught, and this can definitely change the mode of the reactions. So with this, we move to the other subject, that is basically actinide spectroscopy we want to discuss. When I say spectroscopy, the first thing that comes into the mind is the color. And as you can see from here, the lanthanides and actinides also, I will show you in the next slides, that they both are having very different colors, very beautiful colors. And here I will shown that for some of the lanthanides, which are colored or some are colorless, we'll try to discuss that why they are colorless and why some of them are having color. And the question comes here is like, why we see the color first thing. So as we all know that we have a spectrum, that UV spectrum, and there are certain peaks for different metal ions. And suppose you are having peak or absorbance in certain range, according to that, you have some spectral colors. And what we see is not that spectral color, what we see is the complementary color to the spectral color. But before going to the lanthanide spectroscopy or the UV studies or the emission studies, I hope that you have a fundamental understanding of the reasons in the electromagnetic spectrum that we are using for the UV studies or NIR studies. So I assume that you know at least those basic things, you know at least Lambert-Beer law, that how your absorbance is related to the epsilon, to the concentration, and to the path length of the cell you are using for the measurement. So I hope you have the fundamental knowledge of all these things. So we can go directly to the lanthanides or actinides absorption spectroscopy. And as I've shown you that we see different colors, and this is also true for lanthanides and actinides depending on the absorbance lines, or you can see the bands in the UV spectra. But before going to that, let us try to have some information about term symbols. What is term symbol? In general, we all know about the electronic configuration. We have some certain configuration that we know. We have certain configurations. But if you see the configuration, we are having a number of orbitals to fill up with a given set of number of electrons. And if you see that there are number of permutations and combinations are available that can be used for the filling of electron into the orbitals. For example, if you see you are having, let us say you are having a d orbital which is having 10 possibilities, and you have having 2 electrons. So the number of electrons you can say is 2. Why I'm saying 10 possibilities? Because each orbital can have at the max 2 electrons. So we have 10 possibilities. So in these cases, if you see the combination that are possible is 10C2. And from the basic mathematics, you know that if a relation having NCR, it is nothing but n factorial divided by n minus r factorial into r factorial. So for this system like 10C2, what will be there? If you calculate the number of combination or the number of ways in which the electron can be filled in these orbitals is very huge. Here if you see that is 10 factorial divided by 2 factorial into 8 factorial. So if you solve it, you will be getting 90 divided by 2, which is nothing but 45. So here you can say for a simple system of D2, you are having almost 45 combinations that are possible. So out of these possible combination, because electronic configuration can give you all these 45 configuration based on the ways in which electron can be filled in the orbital. But do all these configuration have the same energy, but they are degenerate? The answer is no. Depending on your field, they may not be degenerate. So we know that there are possibilities of different kind of electronic configuration, and each configuration will give rise to something called a term symbol, one term symbol. A term symbol is basically if you have an electronic configuration and you want to understand the energetic part of that configuration, you have to talk about the term symbol because they will relate to the energetic part of the electronic configuration. And as I've written here, for case of europium, which has a configuration of 4f6, its degeneracy it can be lifted either by partially or totally by several perturbation that is acting on this ion, such as the electron-electron repulsion or the spin-orbit coupling or the crystal field perturbation and sometimes the Zeeman effect. I hope you have basic understandings of spin-orbit coupling. That we'll not talk about much of this spin-orbit coupling, but just for your revision, we can have two type of coupling. Then one is called this LS coupling or Russell-Schroeder coupling first, and the second you can talk about the JJ couplings. What is the basic difference between the two coupling schemes is that the first coupling scheme, that is the LS coupling scheme or the Russell-Schroeder coupling scheme, in which what we'll do, suppose we have a system or an electronic configuration in which you are having 2 or 3 electrons, and every electron, suppose you are having 3 electrons, then every electron has a spin S1, S2, S3, and every electron has a individual orbital momentum. And when we talk about the LS coupling, what we do, we sum up all the spins of the electrons, we get a total value. We sum up all the L's to get a total value of N. And this will again couple weakly to give something called J. So here what we do, we individually first couple the spins, then momentum, and then we'll try to get coupling of S and L to give the J value. Whereas in the JJ coupling, which is mostly true for the higher elements, here we start with the coupling of S and L, and here we are getting J for individual electron. And these J couple weakly to give JJ coupling. So mostly these are LS couplings are valid maybe up to atomic number of 30, but after that mostly it is the JJ coupling that takes place. But we'll try to discuss mainly this LS coupling when we are using this term symbol, because this is the way we can always try to explain in a very simple way about the electronic transitions that are happening in lanthanides and actinides. And this is enough for our understanding of actinide or lanthanide spectroscopy. So here I've given you some example that how you can calculate the number of configuration, or rather we say the number of microstates for a given number of orbitals and given number of electrons. So here I've taken an example of F6. And as I've shown you for the D2, here also you can say that since we are having F, we can have 14 possibility of electron arrangement, and then our number of electrons are 6. So the ways in which we can arrange them is nothing but 14, 3, 6. And if you solve this, you'll be getting around 3003 ways. You can just imagine you have almost 3003 ways of the arrangement of electron into the f orbitals when we are having simple and f6 configuration, and all these configurations are not energetically same. So we'll try to see that what configuration has what energy and what is the ground state configuration, and this understanding comes from the term symbol, because the term symbol will tell you about the stability, or you can say the energetics, the energetic leveling of this electronic configuration. How do we find out the term symbol? This is not a very tedious process, and I hope many of you might have gone through this in your BSc or MSc classes. But just for the sake of completion, I've just give a very quick example of F6 which I've taken. So just you see the first line, if you just assume the electron-electron repulsion, you will be having 119 groups of different term symbol. And obviously, if you sum those 119 group, the total number should be 3003. And each term having a degeneracy of 2s plus 1 into 2l plus 1, where s is, again, as I've told, since we are talking about the LS coupling, it is the total spin quantum number, and L is the total orbital angular quantum number. So if you have the idea about the total spin quantum number, you can easily calculate something that is called spin multiplicity, which is nothing but 2s plus 1. And as you can see, there is a one term here. So if you are having even number of electron, you will get an odd parity. If you are having an odd number of electron, you are getting even spin multiplicity. So for 4f6, it is even system, right? You have an even number of electron. For even number of electron, we should get odd spin multiplicity. So in this case, we can get spin multiplicity 1, 3, 5, 7, etc. So let us try to derive term symbol for this F6 configuration, which will be written in form like this, where we write on top the spin multiplicity. L is the total angular momentum that we have seen is sum of L1, L2, L3, that is individual orbital momentum of all the electrons. And J is nothing but it talks about the coupling of L and S, which goes from L plus S to L minus S. It goes from this. So let us see what will happen when you have a system like F6. If you have a system like F6, and if you try, I'll just give you the ground states. And you try like 1, 2, 3, 4, 5, 6. So you should say like plus 3, plus 2, plus 1, 0, minus 1, minus 3. And if 6 electrons fill up, you can start like 1, 2, 3, 4, 5, 6. And if you see the total spin, since you are having 6 electrons and everybody is having a spin of half, so the total spin is nothing but is 3. So your total spin is coming 3. What about the total L? Since you can see some of the L's are positive, some are having negative, means the direction of the orbital momentum is different. So if you sum, you'll find the total L value is coming positive 3. So when you are having S is equal to 3, S is equal to 3, what is the spin multiplicity is nothing but 2s plus 1. It will be coming around 7. When you are having L3, what does it mean? That your angular momentum, as I've written here also, these terms are denoted by capital letter of the Latin alphabet. So when you are having L is equal to 3, you are here. So what we are getting is F is equal to, what we are getting is F. So now, as I've written, the term symbol is 2s plus 1 Lj. So 2s plus 1 in this case is 7. L is 3, which is giving me F. So you can say you have a space group. You have a term symbol that is 7. What about the J number? So as I've shown that they depend on the coupling of spin and orbital angular momentum, and the values can be from L plus S to L minus S. Since again we are having L is equal to 3, S is equal to 3, your L plus S is 6, and your L minus is 0. You can start from 6 and go up to the 0 value. Here I have just shown you the same in the diagram, that 7F and then J value 6, 5, 4, 3, 2, and 0. How this ordering is coming into the picture, that we'll just see in the next slide, that how this order comes into the picture. So we are having these 6 states, and we'll see that how they are arranged. So the ground state term symbol, how to get the ground state term symbol? The ground state term symbol can be easily done by the Ohm's rule. The first thing is the spin multiplicity should be on the largest scale. If the spin multiplicity is same for the two terms, that you are having the same spin multiplicity, then you have to look for the orbital angular momentum. Rule 3 is that if the electronic shell is less than half filled, the ground state has the lowest possible J, and if it is more than half filled, it should be having the highest possible J. Since we are talking about an F6 system, which is less than half filled, so it is less than half filled, so we should be having a ground state with the low J value. And since everybody is having the same multiplicity, you can just arrange them on the basis of J. The ground state should be having the lowest value, that is 7f0. So if you see here, the ground state is 7f0 and others are 7f1, 7f2, 7f3 like that. So with this idea of term symbol, let us try to understand the absorption spectroscopy of lanthanides and actinides. The basic difference between the spectroscopy or UV spectra of lanthanides, actinide compared to that of the d block elements is the involvement of different orbitals. If you see the d orbitals, they are more diffused. When you see the f orbital, they are more centered compared to the d orbital. And or the electronic transitions that are happening in the f orbitals are quite deep buried inside. So their intensity is not very much dependent on the external environment. Why? Because the 4f shells are weakly affected. They are weakly affected by the host ions or the ligands that are present outside, because they are inside this. You have a filled orbital of 5s2 and 5p6, and the f orbitals are inside, so they do not see much of the outer environment, and because of that the transitions are quite sharp when you compare them with respect to the d block elements. But if you have internal comparison between lanthanide and actinide, then lanthanides use 4f, actinides use 5f. And here again we see, if you see the spatial distribution of 4f and 5f, these are more diffused. So you can easily say that the 4f is more diffused. So if you compare the broadness of lanthanide and actinide in a given oxidation state, we can say the 5f may be a little more broader because of the more diffusion compared to the 4f. And they are also more interactive with the ligand field compared to the lanthanide. We'll see some of the spectra of trivalent lanthanide and actinides. But before that, we'll just see this setup. This is, I think, very well known to you, that how we measure this UV visible absorption. We have a cuvette in which we can put our analyte, and this is the double beam UV spectrophotometer, in which we use a monochromatic beam, which will split into two parts, and then one is going through the reference. Reference is nothing but everything except the metal ion or analyte that I want to use. And then we take a reference of that, and since you know the Lambert-Weir law, and since you are getting A from this kind of absorbance, you will get some peak like this, in which your A is nothing but this. And since you are getting A, you know the concentration, you can always calculate what is the epsilon or the molar absorbability. This is, I think, everybody knows, so I will not spend much of time on this. So what kind of transitions are generally possible in lanthanide and actinide? As I've already told that from optical point of view, they are well apart of other elements because they are deep buried orbitals, and they do not participate much as compared to the d block elements into the bonding. And what kind of transition that we can expect in lanthanide and actinides? These are three kinds of transition. One is called intra-configuration transition, the second is inter-configuration transition, and the charge transfer. We'll discuss them one by one. When I say the term intra-configuration, rather sometimes it is also called as FF transitions, these are ideally laboratory forbidden. Why? Because we know that for a transition to be allowed, this should not be 0. This should be +1, plus minus 1 minus 2. Similarly, when you talk about this, the total change in the spin multiple should be 0. So this rule is not followed here because your transition is between F and F. But still we see some transition. We'll see why. And then intra-configuration transitions, here compared to this transition, it is more favorable because it is laboratory allowed. And the third one is charge transfer. We'll see in what kind of actinides we'll get this kind of transition. And here I've just shown you some transition of uranium that we are getting. And if you see carefully, then you see that just by changing the complexation conditions, when you're going from one complex to another complex, there is some change in the absorption pattern, and that is generally used to identify which kind of species is there. And we are also using this kind of pattern to get the stability constant value, or we are getting the information about the strength of complexation. So we'll discuss some of these things in the next slide. So yeah, the first thing is like intra-configurational FF transitions. As I told you, they are pretty forbidden, but still they are seen in the spectrophotometer. Why? Because if you see the selection rule, it is obviously not allowed, but the states are not purely F in the nature. When you see there is some admixture of the opposite polarity into this configuration, you can say there is always some perturbation of this F state wave function with the other orbital, maybe d orbital. So there is some perturbation or some mixing in this state, and because of this mixing, when we say the parity is same, it is not true. There is a bit different parity, and because of that, it is slightly allowed, or you can say the rule is bit relaxed, and because of that, we get this kind of transitions. As they are deep buried inside, they are not affected by the ligand field. I told you that the outer electrons that are present there, they will not allow the ligand field to come up to the orbital, and because of their Laporte forbidden region, or maybe partially allowed region, their intensities are not very high, they are very low, so the molar absorbability of this kind of transitions are not very high. The transitions are sharp, as I've shown you in the previous reason, that since they are deep buried inside and they are getting shielded from the outermost shells which are filled, and some of the example we'll see again in the coming slides. Then we come to the interconfigurational transition, that is FD transitions. As we can see here, the L is following the Laporte rule. So these are fairly allowed transition. But again, as we see, the electron is going from F to D, and this is shielded, but this is not that shielded. Because of that, its broadness is quite on a higher side compared to the intraconfigurational transitions. And since it is allowed transition, so it is also intense transition. And some of the examples are like cerium, tripositive cerium, praseodymium, and terbium. When we talk about the third transition, that is called charge transfer transitions, in what kind of scenario we can do this kind of transition? So to get these above two transition, that is interconfiguration transition and intraconfiguration transition, the requirement is the F should have some electron and should not be zero. You should have some electron because you are trying to excite electron. Even in your FF, you are having some electron here and you are putting electron in this. In your FD again, you are having electron here and you are putting here. But in certain cases, when there is no F electron, in those cases also, if we see some kind of transition that are mainly arising from the charge transfer, and one of the example is uranyl ion, that is U22 plus. If you see, this is uranium 6, and if you see the electronic configuration of uranium 6, you will get a F0 state. So it is a 0, but if you record the spectrum, you'll get a very good spectrum, as I've shown you in the previous slide. So for the F0 system, both the transition, that is intraconfiguration transition and interconfiguration transitions, are not possible, and we are only getting the spectrum that we get because of the charge transfer. And why this charge transfer is happening and how it looks like, we'll see that in the next slide. So when you just compare this, the actinide ion and the lanthanide ion, this actinides having comparatively broader compared to the lanthanides, because the 5f orbital is more diffused compared to the lanthanides. And we'll try to see that how the spectra will look like, and we'll continue this in the next section. And thank you very much.